Welcome and thank you for attending this session on scaling to millions of requests with elastic load balancing. I'm Spencer Dillard. I'm a Senior Product Manager with AWS, focusing on elastic load balancing. Today we're going to cover the basics of ELB. We're going to talk a little bit about example use cases with elastic load balancing and some best practices for testing and evaluating ELB. How many of those in the room currently use elastic load balancing? All right, that's great to see. Thank you. Finally, I'll turn it over to Khwaja Shams and Brett George with NASA JPL to just cover their case, how they used ELB, how they used AWS, and how they delivered one of the largest traffic events in NASA's history. That was covered in the keynote this morning, but covered in more detail here, how they architected their solution, what worked, and let them cover in detail how they went about it. Elastic load balancing can be used in both EC2 and in VPC applications. When you use it in VPC, you have additional option of creating an internal load balancer, and you can add and remove security groups. How many of you are using ELB and VPC today? Really curious what the growth is. Okay, a lot of people. Great. So we'll cover a little bit more of some of the VPC applications later in the presentation. We wanted to talk a little bit about, and a lot of what we'll cover today is how ELB scales up, how does it handle traffic, how does it adapt, what makes it elastic, and help give a little better understanding of what's happening underneath the hood as you're running your application. What is it doing to scale and meet the needs of your application? It relies on DNS for scaling. For those of you who are using ELB today, probably aware of that. As resources are made available to your application, there are more IP addresses added to DNS. We'll cover that in some detail, but it's completely dependent on DNS to be able to provide the changing elasticity, the changing resources that are allocated to your load balancer. When you use a single load balancer, it can span availability zones. So it is a regional entity. You create a load balancer. It can support one or more availability zones in a region. You can ensure that you need to have instances available in the zones that you enable. So if you enable 2 zones, you should have instances running in those zones. Otherwise, you really can have a false sense of confidence about the availability that ELB is providing. If you enable 3 zones but have instances running in 1, we see a lot of people who think that that is giving them availability when really they're still at risk because their application is really only running in 1 zone. So it's important that as you think about ELB providing that availability and that elasticity, that you also design your application to be able to work well in that context, to be able to run across multiple availability zones. ELB supports both layer 4 and layer 7 load balancing. This is one of the areas that we've seen a lot of confusion on, that people think it is a pure HTTP layer 7 load balancer. In reality, ELB supports layer 4, either straight TCP load balancing or with SSL offloading, still layer 4 or layer 7. When you use layer 7 load balancing, it can be HTTP or HTTPS, and the load balancer is essentially terminating the request at that point. When it does so, it adds headers for the X forwarded for, and you can use sticky sessions through a cookie-based implementation. One of the key things that we've seen a lot of growth in ELB in and a lot of usage, and I'm also curious how many people are using it for this, is really to offload SSL and to leverage ELB to provide the computational support for SSL decryption and in some cases re-encryption. And we're seeing that be a really huge use case for ELB and for people trying to reduce the cost of their applications and shift the burden of SSL decryption onto ELB. Again, I'm going to do a little quick survey. How many people are using the SSL aspects of ELB today? All right. Decent sampling there, probably about a quarter. That's about what we've seen overall. One of the key points of ELB is that it's integrated with a number of the AWS services and applications. It's really intended to be simple. It's intended to be very easy to use and let you use all of AWS that makes sense in the context of ELB. So as you use ELB, the AWS Management Console provides nearly complete support for everything you can do with your load balancer. Allows you to change listeners, to add instances, remove instances, add zones, change your SSL certificate, control the ciphers and protocols that are presented to SSL clients. It gives you full control over the application. Of course, you can still use the command line tools, the API, the SDKs, all of that is available. But the console has really grown a lot in the past year to provide pretty full support for all the features of ELB. A really key feature of ELB is that you get out of the box a number of features through CloudWatch to be able to understand how your load balancer is behaving, how your application is behaving. Specifically, some of the key metrics that ELB provides are latency of your backend instances. So what is the response time of your instances? How are they responding? Are they overloaded? Are they underweighted and responding too fast? Maybe you can reduce capacity. It also provides the request count, how many successful either TCP connections and responses or HTTP request response have been completed, as well as HTTP error codes and status codes. So you really can get a pretty good overview of your overall health of your application through the load balancer, including how many healthy or unhealthy instances are currently running behind the load balancer. All of that is available through CloudWatch today. When you create an ELB, there's a hosted zone that is created with Route 53. This allows you to create an alias to your load balancer. So if you need zone apex or root domain support, you can use Route 53 for that. You can use a CNAME, which is how historically most users have done it, is to create a CNAME to the load balancer's DNS name. But you don't have to if you prefer Route 53 and use the alias feature. You get a couple of added benefits of clients not having to get the CNAME and then re-resolve that, slightly better response time in terms of that cycle. And you get added benefits of Route 53 features, such as latency-based routing, being able to string together multiple regions in one domain, a number of features that come with the Route 53 integration. While you can directly register instances with Elastic Load Balancing, really one of the key features that customers use very heavily is autoscaling. Autoscaling makes it just super simple to be able to ensure that you have the capacity for your application, to be able to ensure that your application has enough instances, that they're not overloaded, to be able to scale up and down, and really makes it simple for you to do nothing more than define your autoscaling group, register it with an ELB, and off you go. Your application is running. Finally, there's IAM support for your SSL certificates. So you can upload your SSL certificates and private keys through the AWS console or through the IAM tools directly. When you do so, you can apply them and add and remove certificates to your load balancer, update them through the console. Really makes it very easy to keep them updated, be able to apply updates easily without a lot of effort. So a couple of architectures that are common with Elastic Load Balancing. We'll walk through a few, and then some of these will be covered in greater detail with how NASA and JPL used ELB. When you use it in EC2 or in VPC, you can enable multiple availability zones. One of the easiest ways is to use autoscaling and let autoscaling launch instances, again, with ELB. So those instances in those groups could be autoscaled. Really makes it very simple to add and remove zones. So if you want to move out of one zone for whatever reason, switch to another, go from 3 zones to 2, very simple change to add and remove a zone. In VPC, the behavior is essentially the same, but in VPC, there's a slight subtle difference that you register subnets. So you're specifying the subnet that load balancer will put an interface into that subnet. It can still be public-facing, but one of the advantages of VPC, and this came out earlier this year, is the ability to use internal load balancers, which enables an architecture more like this that is shown, where you may have a public-facing load balancer, and that load balancer is open to either the internet, or it may even be open only to a subgroup of CIDR blocks, maybe open to just your home office, for example. But the internal load balancer has no public IP. It only has private IP addresses, and can only be reached from within your VPC, from within your subnets. So a common application that we're seeing more and more, and was a very heavily requested feature from customers, was the ability to do internal load balancing so that you really can tier your architecture, but still make it very easy to use autoscaling to scale up back-end services. whenever ELB is talking to its backends, it will always use the private IP address of your instances. So I wanted to walk through a couple of what happens when ELB scales, explain a little bit about the strategies, what it does to add capacity to your load balancer, and how that works. And then in a minute, we'll talk about some testing strategies. How does this behavior affect your application? How does it affect how you think about architecting your solution? So when you first create a load balancer, there's an initial amount of capacity that's allocated. So in this diagram, the black area basically shows the IP address that's currently in DNS and the resources that have been allocated. So there's a certain default level of allocation of capacity when you first create the load balancer. What happens after that depends on your traffic and it depends on time. And there's fundamentally two dimensions that we're looking at to decide when to scale up, down, out, or in. And ELB can take any of those actions. So scaling out is essentially horizontal, adding more IP addresses. Scaling in, reducing IP addresses. But we may also scale to higher performing instances or lower performing instances and nodes to make sure that we have the right capacity for your application at that point in time. So when you first create an ELB, for example, you might have capacity in each zone that you've enabled. So in this case, we've added 2 zones, and an initial capacity is allocated. As more traffic comes to your load balancer, new IP addresses will be added to the DNS record. It's important to note, and something that a lot of people, I think, have had a little bit of a challenge with, is that that old capacity doesn't immediately go away. In fact, clients can continue hitting the old IP addresses for a period of time because ELB really tries to do everything it can to make sure that that traffic gets to your application. Historically, one of the things that we had a lot of feedback on was that it scaled too rapidly from the point of view of moving IP addresses around within, say, an hour, and it was too rapid for some applications. So we made a number of changes over the past year to really change this, and that capacity could be around for hours, depending on your traffic and your clients. It could be around for days. But we're really trying to make sure the traffic gets to your application. So at this point, ELB has scaled. It has scaled up, and it's put 2 new IP addresses in DNS, as identified by the black areas on there. The yellow is still running, still around, able to handle traffic. This gives us an extra added boost so that at moments of scaling, ELB doesn't go from one set of resources to a completely different. It's really adding capacity, and then eventually the older capacity will be removed from the load balancer. As traffic continues to flow into the load balancer, we'll continue to add more capacity. This, again, can be scaling up or scaling out. The IP addresses will keep getting reflected in the DNS record. So it's really critical that as you build your applications, there are a couple of factors that come into play. The DNS record has a 60-second TTL, a time to live. So clients that cache DNS permanently can have a very bad experience with ELB. It's part of the reason why we leave that old capacity around is to reduce the risk of this happening. But as we do that, the DNS record gets updated with a 60-second TTL. Clients need to re-resolve to take advantage of this new capacity. It's less of an issue in the real world, but it is an issue, especially in synthetic testing, where a lot of these things come into play when you're trying to test and evaluate the load balancer. So as the load balancer goes on, as your traffic subsides, that old capacity will eventually be removed. And you may be at 4 IP addresses, you could be at 2. There's really not a limit per se as to what the IP addresses could be returned. The DNS record will return up to 8 IP addresses today. So clients can try to connect to another one if for some reason they can't connect to one of the 8 that are returned. But there may be many more than 8 behind your load balancer at any point in time. It really depends on what's happened to your traffic. So there's a lot of different applications and patterns that we see in customers. So one of the things we did was take a snapshot of a couple of customer applications, and we really wanted to kind of give an example of what they experience, the types of traffic patterns that work really well with ELB. So for example, a fairly common application, and we've changed all the values to protect customers' identities, and put them on a similar scale, but basically very consistent traffic patterns. This is really easy for elastic load balancing. Fundamentally, what it has to provide is making sure that any node, any IP address that's been allocated is running. It's responsible for replacing any node that has a problem or fails, putting it back in service, and ensuring your application continues running. A very straightforward application, not a lot of need for auto-scaling day-to-day. It tends to be more about auto-scaling to ensure that there's a certain number of instances running. And the load balancer is really just handling the traffic pretty seamlessly in these cases. So an alternate pattern that we see quite often, too, is kind of the 9-to-5 type pattern. Customers that every day are scaling up, their traffic is increasing at 8 or 9 in the morning, it's ramping up every morning, and then it continues throughout the day, and then eventually starts declining and repeats the next day. We have a lot of customers in this case. ELB handles it really well. This is over a period of hours that these ramps are increasing. Very normal pattern, and the load balancer will generally scale down fairly conservatively to protect against this type of pattern. For those who may have used it 2-3 years ago, we scaled a lot more aggressively, and there were some issues here. Another area of feedback that we had was really making it more stable in terms of the capacity we allocate and less impactful when you have these daily cycles. And we've really had good feedback so far that the changes we made to adjust the scaling really have fit the applications much better that people are running. And finally, we see cases where there are spikes in scaling. This is still okay. This is still a matter of an hour or two type of scaling, big increase. For example, an email goes out, and it's a gradual ramp up in traffic. This works really well with the load balancer. It can scale up roughly at about 20% increase in traffic every 5 to 10 minutes is no problem for the load balancer. In a case where the load balancer is less of a good fit, and I think it's important that people understand what you can do in these cases, and NASA will cover some of these aspects as well. The load balancer will have a massive spike, for example, a concert, and we see this type of scenario decently often. An email or a tweet goes out for a concert, and the load balancer and the application goes from 100 requests a minute to 1 million requests a minute, and it does so in 30 seconds. That's a little harder case. And when you're planning for that type of application, there's a couple of things you can do. So one of the easiest solutions is if it's highly cacheable content, you should definitely consider looking at putting CloudFront in front of the ELB and using ELB as a custom origin is one of the easiest solutions to providing that type of a solution. Alternatively, if you know that that type of message is going out, you can drive traffic to your load balancer and cause it to scale up and be ready for that traffic when it comes. So finally, walking through a couple of considerations as you test and evaluate your load balancer. A key part is the ramp-up time. As we went through in the scaling approach and what ELB does to scale, the load balancer will add capacity. And it does that by monitoring the traffic to your load balancer. So roughly over a 5-minute window, it's looking at how much traffic has gone through, has it breached a threshold at which we need to scale, and if so, it initiates a scaling activity. This takes a little bit of time, and it can take anywhere from 5 to 10 minutes to scale up each step. So if you are testing or evaluating the load balancer, if you bought a hardware load balancer, a common practice might be to suddenly throw 1 million requests at it and see if it can handle it. It's a very different approach with ELB. You want to ramp that up over time to get to what you expect your steady state to be. Your application is going to also, you would want to do that to drive the traffic so your load balancer is ready when you flip it to your domain and are ready to use it in production. Typically, you want to use a factor of about an increase of 20% every 5 minutes is sufficient for it to continue to scale. And that's really a general guideline. The performance will differ if you're using SSL, if you're offloading, if you do not have persistent connections. There's a number of factors. So when you're testing, it's important to find out the right balance there for your application and your types of clients. As we covered a minute ago, the initial allocation of capacity to your load balancer may not be right for your application. It'll scale up over time, but if you leave that load balancer alone, if you just create it and you walk away and 2 weeks later you decide to run your load test, it may have scaled down because there was no traffic for a week or two. That's going to be generally a poor experience if you then turn around and throw 1 million requests at it. So you need to both ramp up your traffic, and also, if you're going to test it within a day or so of when you've created it. Otherwise, it may have scaled down from the initial allocation. A key point in your testing is to make sure you understand how your clients are testing. We see a lot of cases where people are frustrated or confused because they did a load test and it was 1 or 2 clients that were sending hundreds of thousands of requests, and they weren't re-resolving DNS, and it was only, say, 2 clients. A very common problem here is older Java-based applications that may, by default, have the DNS caching set to permanent. When you do that, essentially the load balancer is scaling up. It's trying to add more resources, but as it is, the clients keep using the same original resources that were allocated. They're not adapting as the load balancer is adapted. So it's really important that you figure out how to test with distributed clients, multiple clients, and that those clients are re-resolving DNS. One of the really effective strategies that's been used heavily with ELB is something called bees with machine guns. That's an open source Python-based solution. We use it ourselves as well for some testing. It's very effective at being able to launch a number of instances, use them to throw traffic at a load balancer, ramp it up, have some control, and do a really good job of simulating a fairly real-world experience. Bees with machine guns. It's a very odd name. I didn't name it. I think it was the Chicago Tribune, if I'm not mistaken, that came up with it. And it's on GitHub as well. But it's really solid application for being able to use it. In fact, there is a CloudFormation template that is available on the CloudFormation site that lets you fire up a bees with machine gun stack and point it at a URL in a few minutes. So you can really get up and running very easily. As you're doing your testing and evaluation, it's obviously important to monitor your environment. It's important to make sure you know how you're doing. You can use CloudWatch for that, and you can continue to monitor both the load balancer and your application instances throughout your test. I'm going to wrap up and turn it over to Brett and Khwaja to go through NASA's use case, NASA JPL.
Thanks, Spencer. Thanks. All right. So my name is Khwaja. This is Brett. We're from the NASA Jet Propulsion Laboratory. And we're going to talk about the landing night and the video streaming solution that we put in place. Essentially, just a little bit of a background. Curiosity is a 1-ton rover that we're about to land on the surface of Mars. And we knew that the world was going to be excited and watching us, but we didn't exactly know how much capacity we needed. We anticipated our traffic to be anywhere from 200 gigabits per second to over 1 terabit per second. And it was a tough situation for us to be in because we didn't want to go and start provisioning more capacity than we really needed, but we also didn't want to have infinite capacity or virtually limitless capacity at our disposal. So with that in mind, we worked very closely with folks at Amazon and the engineers at JPL. The most important part of this story is that we had 2 weeks to deploy the solution, to come up with, build, design, test, and deploy the solution because we wanted to have another streaming outlet for us. And within 2 weeks, multiple engineers at Amazon worked with us, as well as engineers at NASA, including myself and Brett. So folks like Jamie Kinney and Miles Ward helped us significantly in designing this architecture and putting this out there, and we're going to take you through what this architecture is about today. But before that, we want to get into what we were trying to accomplish. We were trying to accomplish ELBs on steroids. We wanted to get to terabits per second of traffic, and we wanted to have a horizontally scalable application that can sustain hundreds of gigabits per second. And to do that, we used some tools, Route 53, for instance. So Route 53 allows us to get some very neat features to actually put ELBs on steroids. So first of all, with weighted round-robin support in Route 53, we're allowed to use multiple ELBs across even multiple regions if we wanted to. So if you wanted to, you could have an ELB in the East Coast, an ELB in San Francisco, an ELB in PDX, which is Oregon, as well as an ELB in Ireland, in Tokyo, in Australia. And you can connect all of those together with weighted round-robin such that if an entire continent goes down, you can rapidly update your Route 53 configurations and take the regions that are suffering outages completely out of the picture within a matter of 60 seconds. We also can use Route 53 to use latency-based routing, which means that users from Virginia, when they resolve the DNS entry, they get directed to an ELB in the East Coast. When users in LA resolve the same DNS entry, they get directed to the data centers in San Francisco. And more importantly, a lot of people around the internet are actually combining the weighted round-robin and elastic and the latency-based routing to come up with some very powerful solutions to augment what the ELB can do for you. We also used CloudFormation very extensively. When you start having a very complex architecture, it's very helpful for us to be able to express that complex architecture succinctly and be able to deploy that entire architecture with a click of a single button. It's also very nice for us to be able to clean up those instances cleanly, and Brett will go into a little bit more details on that. And even more importantly, it's important for us to understand the differences between the regions and the availability zones. It's important for us to understand that each availability zone is isolated, it's fault isolated, so that if an ELB is actually a highly available service that spans across multiple availability zones. So if in case an entire AZ goes down, you can still automatically stop your instances in the particular AZ and still service your requests to the users without letting them feel any outage. And then with Route 33, we're actually able to do multi-region mission-critical applications.
Yeah, so I'm going to go ahead and go into the detail about how we actually implemented this solution using all these technologies we just talked about. I know this is mostly a talk about elastic load balancers and their function and their usefulness, but it's really hard to talk about just them isolating or working by themselves, because I'm sure you all know we tend to use elastic load balancers as part of a complete solution. So I'm going to go into how we use that. A little bit of backing up a little bit. Khwaja mentioned that we had 2 weeks to work on this. It was actually a little bit less than that. Probably more like a week and maybe a day or two. Yeah, there you go. And on top of that, this is a completely new arena for us. So this whole video streaming solution, we hadn't done that before. None of us really had experience. So we had amazing help from Jamie Kinney and Miles Ward at Amazon. They're great guys. They helped us out. And we got all that done within a week. Not to toot our own horn, but I think it's testimony to the fact of how easy the tools were to use and just how successful we were at being able to use those tools quickly as somebody who had never really used them before. So the problem that we were facing is that we knew we wanted to deliver this video streaming to the public, but we had no idea, one, how much traffic we would have. We just had no way to estimate this. Two, again, not having the experience to do this, we knew that we had to be able to scale dynamically, going back to the point of not knowing how many people are going to view this.
And it's important to note that we had to scale up as well as scale down, because right at the peak of the Curiosity landing, everybody tuned into our system. And then right after we were done, within a few hours, we tailored off to almost having, very little traffic.
Yeah, and actually you're going to see that. So what I'm going to do is I'm going to talk about the details of the actual implementation, go over some of the tools that we use and how we tested our solution, and then actually talk about how it actually ended up working out. And you'll see some of the graphs. It's pretty extreme how traffic spiked and just tailed off. I mean, it's kind of to be expected. People were mostly concerned about the 7 minutes of terror. Although, how many of you had an entire day landing event party at your place? Anybody? One person? Yeah, so most people were tuned in for that one particular moment, and rightfully so. It was the most exciting part. So our solution was comprised of, at the very bottom, Adobe Flash Media servers, EC2 instances deployed into a few different availability zones in a few different regions. US West 1 and 2, US East, and also in Europe. These servers were basically receiving video that was being pushed out to them from our Wirecast stream, and they would be acting as the origin video servers. So on top of that, we would deploy CloudFormation stacks. The reason I kind of have CloudFormation stacks being a separate thing here is that you can think about ELBs being, they essentially are the backbone of our solution. They actually are what made it possible, but CloudFormation is the glue that held everything together, that allowed us to integrate all these services together and actually allow us to deploy these stacks of cache nodes easily and quickly into as many availability zones and regions as we wanted. So we would deploy a stack into availability zone. At the very bottom of that stack was a layer of Nginx cache nodes. These Nginx cache nodes would reference one of the Flash Media servers, and actually that diagram's not entirely accurate. It would, oh, sorry. It's not entirely accurate. The tier 1 cache would actually reference multiple Flash Media server instances, but what it would do is it would prefer the instances that are in its own region, just to provide locality. On top of that, we had a second layer of Nginx cache. This one would be much larger. The first layer only had a few nodes serving as a cache. On the second layer, there was actually up to 40 cache nodes, so it was kind of a fan-out caching scheme. And these were actually part of an auto-scale group. So we had it configurable, but we generally set the auto-scale parameter so that it would be the minimum of 40 and a maximum of 40, so that we just wanted 40 nodes in the stack. And if one of them went down, auto-scale group would replace it automatically without us having to worry about it. And then these nodes referred to the tier 1 cache nodes, which then in turn reference the Adobe Flash Media servers. And as Spencer was already talking about, elastic load balancers were what actually were routing all the traffic to that second layer of cache nodes. One thing to mention, and you'll see this in the graphs about the traffic, we actually had to have them pre-warm some elastic load balancers for us. And what that means is that slow ramp up to get them ready to accept a high volume of traffic, because we knew come landing event that we were going to get a huge influx of traffic. So we didn't really have time to have like this gradual ramp up naturally. And we were able to work with them and actually get that taken care of. Then finally, Route 53 was the final level. So when we deploy a CloudFormation stack, the elastic load balancer would then be attached to an alias in Route 53 and we use weighted round robin. So it'd be given a weight that was proportional to the stack's ability to handle traffic. So that way traffic was routed fairly between all of the different stacks that Route 53 knew about. And then once we had the CloudFormation stack up and working, deploying it into another region or availability zone was as simple as a few clicks of a mouse. Then boom, we just launch it into US West 1B. And we actually did this multiple times during the actual landing day event. CloudWatch proved very useful while we were doing a lot of our testing, and actually even while we were monitoring during the landing day event. It provides an amazing, easy-to-use tool of just being able to watch your traffic and being able to aggregate that traffic using different metrics.
And also to be notified if something goes wrong and get a text message on your phone if your elastic load balancer or your instances have gone down.
Yeah, so we could use it to actually monitor how an elastic load balancer group was performing. Using the web console, we could visually inspect how these different types of EC2 instances, autoscale groups, and ELBs were performing. And like Khwaja just mentioned, there were alarms that we could set. We didn't actually take advantage of that because, we were kind of glued to our seat watching these the graphs as they were happening live, just ready to act if we needed to. But going forward, this is an extremely valuable tool that we definitely wish we could have, in the short time span, taken better advantage of. So for benchmarking, obviously we didn't want to go into the landing event cold turkey. We were pretty sure it was going to work, but we wanted to prove to ourselves before the event that it could actually handle the traffic that we wanted. And we were shooting for about 25 gigabits per second per stack that we deployed. We partnered with Soasta, who actually specializes at testing at scale your distributed solutions or your website or whatever else you want to throw at it. So what we did is we worked with them to test an individual stack and just have them throw a ton of traffic at it and see how that would work. Now, it wasn't just any old traffic. We actually came up with a script that each of their worker nodes would run that more or less simulated a client requesting 4-second chunks every 4 seconds. So using that, we were actually very successfully showed that this one stack that we designed was actually capable of handling more than 25 gigabits per second. So we more than hit our mark. And it was extremely successful, and we were obviously very happy. And that gave us the confidence to go forward and actually do this on landing day.
And we also did a little bit of load testing on our own before we went directly to Soasta. So there's a lot of tools available to you to test your own infrastructure. So bees with machine guns that Spencer mentioned, but also JMeter is a very helpful tool in generating a ton of load and just slowing that towards your ELBs and just to see how it performs. You can also set it up so that it ramps up slowly so that it actually simulates the real use cases that you have in your applications.
Yeah, and also worth mentioning, while we were doing this testing, we were able to kill nodes within that auto scale group and just watch how the traffic fluctuated and to compensate for that. And needless to say, it was really effective. The auto scale group was able to get new nodes online within like a minute after the old ones died.
Right. And there's two things actually that are happening there. We had a very aggressive health monitoring policy on our ELB. So as nodes were becoming unhealthy, as soon as we go in and terminate a node, the ELB would stop getting the health responses back from the node, and it'll automatically stop routing traffic in that direction. So it was a very seamless transition for us to just kill a node and maybe lose a couple of requests that was handling at the time, but then immediately after that, within a second or two, ELB will stop routing traffic towards that node.
So this is the results. These are graphs that I took, basically screenshots of CloudWatch graphs from after the landing day event. I'm not really sure what that anomaly is right there on the left, but in general, if we look through all these different graphs, you can see a pretty huge peak in traffic around the landing time, which was, if I can convert from UTC to Pacific time, was that like
2012, 10:31
there
p.m.
you go. So you can see we had a few, like this was 25 gigabits per second of live traffic, 10 gigabits, 40 gigabits, 26.6 gigabits. So all in total, and this is just in US East, this gave us 110 gigabits per second of traffic at a peak. We don't know how many live viewers total or how many live unique viewers total, or maybe we do have that number, but we do know that we had at least 120,000 concurrent viewers at one time. That's assuming that they all watch the highest quality video stream, which is probably not the case. And here you can see how the actual FMS, the Flash Media Server origin nodes were impacted. So when we have 40 gigabytes or 40 gigabits per second of traffic hitting the tier 2 cache, it's only about 42 megabits per second on the actual Flash Media Server. So it worked really, really well in terms of getting that traffic just efficiently and not bogging down our servers at each level. And this is one of the other US East Flash Media Server origins. So yeah, this is our solution. This is what we came up with in about, it was a week and a half. It was very useful. I think we learned a lot from it. It was a very pleasant experience, I would say. Yeah, it was a great learning experience. And one other thing to touch on is CloudFront, which I think Kwajik can.
Right. We also used ELBs extensively behind CloudFront. So we had a lot of static content on our site, on the Mars site, that we were serving directly from S3. But at the same time, there was a little bit of dynamic content that was also coming from the ELBs. So we used CloudFront behaviors to route specific URLs towards the ELBs to handle our dynamic content while routing all the static content back to S3. So it works really well to actually use the CloudFront behaviors as a caching layer, and you can set up different behaviors for each type of your URL, which work nicely. Right. And I would say that there's a lot of documentation available online. There's a lot of support in the community for ELBs, and there's a lot of case studies that you can reference to inspire your next solution. The one thing at JPL that's actually empowered us top down is that there's support from every level of management for us to build innovative solutions in cloud computing. Our CTO, Tom Soderstrom, in the audience here, has been supporting the cloud computing work and envisioning what cloud computing can do for us over the last 4 years, as well as every developer, including Brett and myself, have been working hard and tirelessly to deploy the latest solutions onto the cloud where we see it fit. So that's been our secret to our success, and we look forward to deploying even more applications. At this point, we'll take any questions that you might have in the audience.
Yes. Oh, sorry.
Cost effectiveness. Sure. Tom, do you want to say something about cost effectiveness? Our live video streaming solution actually ended up being very cost effective for us because we didn't have to sign a contract with a vendor pre-provisioning capacity. We didn't have to say, we're going to scale to 200 gigabits per second or terabit per second. Please give us this much capacity, which is very typical with some of the content distribution networks. We were actually able to basically pay for exactly the amount of bandwidth that we used, and there wasn't a charge for having using more bandwidth at a given time and then shrinking down. There was basically charged for the total number of bytes transferred. So at one point, if we were transferring 1 gigabit per second, and then the next point we were transferring 500 gigabits per second, it would have costed us exactly the same depending on the total number of bytes that were transferred. So this made a very effective cost model for us. Furthermore, the way that Brett designed his CloudFormation stacks, everything is parameterized. So each of these stacks has a parameter for how big you want the layer 1 and the layer 2 caching servers to be. So when the rush was over, when things calmed down, Brett basically took off all the really large CloudFormation stacks and then deployed a very small CloudFormation stack that is basically serving the rest of the traffic from here on out. And it allowed us to very cleanly, remove all of the infrastructure and then deploy the exact same infrastructure, at least the exact same template, but just in a smaller, more compact, and more economical setting.
Right.
You got a question?
Compare with the generally CPN provider solution, what benefit you get is you do this from scratch yourself?
Well, for me, it was a learning experience. But no, I think Quadra can speak better to that.
It's the ultimate flexibility that you get. If you've got a custom application, there's a lot of solutions available, by the way, for streaming. CloudFront also does an incredible job of streaming. But if you have a custom application which you want full control over, and you want to be able to dynamically put your origin servers behind different regions and have ultimate mission-critical availability, this works out really nicely for us. The cost effectiveness was the other aspect that we had compared to the traditional CDNs, because this is really a pay-per-use model. Remember, if you want to do 100 terabits per second of traffic, can you imagine how long it will take you to set up a contract with a content distribution network? Given that you have like an Amazon account, you can just go in and provision this capacity, set up like a form online that says, hey, can you please pre-warm my load balancer? And all of a sudden, you're done. You're ready to go. You're not dealing with the pricing negotiations with contracts and legalities. You're set and ready to go as soon as you want to. In the back?
Yeah, I can't really see.
So this was the, so we're basically doing HTTP streaming. So the clients would come up and they would say, please give me the next 4 seconds of traffic. And then they would just keep doing this repeatedly. It's basically HTTP, pull requests saying, hey, can I have the next 4 seconds? Can I have the next 4 seconds? And so on. So the users who went to one of these failed machines that we might have killed dynamically would basically, at the worst case scenario, experience like a second of jitter because the media player on their end will just retry their request. Right? And most of the time, these media players have buffered enough such that if the request failed, they would actually seamlessly go back and get it again from the other server without even letting the user know that something nefarious had transpired in the middle. What's that? So can you repeat your question, actually?
No. Not that we've heard of.
So the question was that, did the user see any 404s? And the answer is no, because the users downloaded the main page, and the main page had a JWP player that was then basically going and behind the scenes fetching all the frames as necessary. So the JWT player basically encapsulated the logic and the user experience of fetching the frames and so on.
Waiting for that one guy to step forward and be like, hey, I got a 404. Yes, sir? Oh, so you mean like as far as who has access to like maybe launch a stack into a region? We use IAM credentials. I think like this is the most common access pattern for AWS. Obviously, I was kind of given godlike control over the deployment, or at least that particular account for the time being, because I needed to be able to start up what I needed to start up, stop what I needed to stop. But in general, those credentials are kind of highly guarded. So if that answers your question.
Right, so basically, how do we control access? Because this is a complex environment. We had video streaming solutions, we had content management systems, we had static content, dynamic content, and a lot of different teams working on all of this. Brett did maintain godlike permission, and so did one other person in my team. But I think your question can also be phrased, who had access to screw everything up, right? Even though we maintain godlike privileges, we are very judicious with the use of IAM credentials, right? So there are people for whom we have generated just CloudFront IAM keys. There are people for whom we have generated just EC2 launching capabilities, and there are people for whom we have given auto-scaling privileges and CloudFormation privileges. So a random person working on a CMS using the same account does not actually have access to bring down Brett's CloudFormation
that's
template.
a good point.
And if you weren't, you really should have been using your own IAM credentials that had very limited access. But we're last minute. details there. But for operational efficiency and for real mission critical operations, it is imperative to use IAM credentials to actually limit the amount of access. It's also good practice, right? Because you want to limit the exposure in case any of these credentials are lost. So yeah, you want to be very judicious with how you use the root IAM credentials.
Sorry. Oh, actually, yeah, let's have you guys.
How many load balancers was in play per region? I know that they're not cross region, but you have to cross.
Right. We had, I don't remember the exact number, but we had multiple load balancers warmed up per availability zone per region.
Yep. So we had about a dozen load balancers that were pre-warmed, but they didn't have a CloudFormation stack connected to them.
Right.
So we would provision the stack, attach it to the load balancer, attach the load balancer to Route 53, and then register it into Route 53 as a CNAME.
Yeah, and the way that worked is that we would actually, as a parameter to the CloudFormation template, we would pass in the load balancer that we wanted it to attach to. So that was a little bit of manual control over that.
Right. And our strategy was, by the way, if we ran through the 12 pre-provisioned load balancers, we would be calling our premium support line and saying, hey, once we are at 9, we've only got 3 more to go. We would be calling our premium support line, getting the ELB guys on the line to, pre-warm more capacity as needed. That's what we verified with the testing with Soasta.
Yeah.
We tested an individual stack with just one load balancer to see how big each stack could get.
Yeah. Yes, sir. We didn't have that happen, so.
We didn't have that happen, but we had an operational plan. So we used Route 53 with weighted round robin. So if we noticed that a particular load balancer was misbehaving, or if, let's say, a region was going down or an AZ was going down, we would basically just go, the plan was to go to Route 53 and take that load balancer out of service. So that when the Route 53 DNS resolution is happening, it's not advertising this load balancer to anybody else. What was that? Well, so here's the thing. The whole stack is there, but you can cut the stack from the production just by updating your Route 53 record, right? So as soon as you update the Route 53 record, we can leave the stack running to go diagnose what actually happened, right?
Well, we can just deploy a new stack, probably against a different load balancer.
Right. Yeah. But we would do our analysis. We will try to understand what actually happened at this point. We could basically deploy another load balancer. That's actually one of the beauties of cloud computing is that you can just replicate your environment again from production to staging to development, and then from production back to staging if something goes wrong, and just replace it right away.
Right.
So we, for Route 53, we're using TTLs of 60 seconds. Now, we're assuming that the intermediate caching is well behaved. I'm not sure how long it would take ELB to beef up its capacity, but that really depends on the pre-warming arrangements that you might have had.
In this case, there's an unusual requirement, right? We had trying to hit a massive level of traffic. That's pre-warming because it would have scaled there, but there just wasn't time to let it scale there, given operations status. So it was scaling. Basically, they would let us know. We would overscale it to make sure it was ready for the service to go. For most applications, it's not needed, but if you're running everything per second, then you may need that.
Right.
That's right.
Yeah, it's going to scale. Basically, it's monitoring traffic. And as traffic is coming in, it's scaling up and adding more instances and adding more resources. It can be multiple. It can also move to different instance types.
So that whole
there's
process,
lots of different ways we can use resources there.
from a customer's perspective, that whole process seems to be automated. And then, for special arrangements, we can, pre-warm them if, we know that at this time we're going to hit this kind of traffic, so on.
We have 30 seconds left, so I think we're going to have to hold questions. And if any of you guys want to come talk to us about our solution afterwards, feel free. Come find us and talk to us.
We'll be around all day today, all day
There might
tomorrow.
be another slide.
So feel free to come by and talk to us.
You want to talk about this?
Just a few follow-ups. So some documentation, links. I doubt that anybody's going to manage to copy that in the next 15 seconds. But it will be on SlideShare, so you can refer to that. Thank you. Please do fill out an evaluation form. We want to get feedback on all the sessions and how we did and what you'd like to hear more of. And that is it. If you want to talk to me specifically about ELB, I'll be at the booth between 1 and 3:30 today. So thank you for your time.
Thanks guys.